Now time for electric field and flux. Here is the tutorial. So, what single line could you specify location? Yeah, so I would say if I could think of a number of ways, but one that's easy to define and also easy to reproduce is I take I start at the center of the card and I draw a line that's perpendicular to the plane of the card. And so if I say it's always in the center and it's always at right angles, then it's always easy to understand. And it could point up from the table, or it could point down into the table, either way. So there is a little bit of leeway. And we'll call this vector n, and we'll also call it the normal. So we have a vector called the area vector. What does the direction of this vector represent? The direction represents anything you please. I have no idea about this stupid question. I know what they're driving at, I think, or I know the ultimate answer, but I don't understand what they want in this particular case. So the direction can represent anything you want it to represent. So it's your choice. The magnitude I would expect, if it's an area vector, I expect it to represent the area of the surface. Okay. So describe direction and magnitude of the area vector A with this sheet of paper. Well, the magnitude I'd expect to be 64. The direction, I have no clue. Idiotic question. And they want you to pay $85 for this workbook, guys. Well, but let's define a vector A better way than they did and call it the magnitude of the area times the normal vector. So now we know to put it in the middle, and we need to put it perpendicular to the surface. And right, any direction you please, and location wherever the hell you want to put it as well, the initial answer. Because there's just no way of knowing. It's completely arbitrary at this point. So now, if we want to extend our definition to one of the little boxes, well, the area, I don't know, we could call it 1 if you like. Excuse me. And we can put its own normal vector in the very center of the box, little box, and have it, of course, point at right angles once again. Okay, now, if I fold it into a triangle, or fold a piece of paper into this triangular prism, then no, we need 3 lines at least, because we couldn't have one line satisfy the condition that we've defined to this point, although we defined it, not but their questions didn't get us there. So the only way we'd know is if you had somebody to ask, like the professor. So it means we need an umpire in this game, or we can't go any further. So anyways, the next one was the tube, and they don't ask you if you can use one line to represent the tube. In fact, you can in a way, but the A vector for the tube shape, I guess, you could say would be at, why is it my, there we go. So you could pick, like, in the Z, this, in a cylinder, this is the Z coordinate, so you could pick halfway, and then it would be parallel to a radius vector at that point. But it could be anywhere in the azimuthal angle phi, because remember, in a cylinder it's r phi z, or sometimes theta. Azimuth angle, usually rotation around something, is usually called the azimuth, and usually use phi. What else? But in this case it said dA, so sure, we could pick one, and if we pick it small enough, it'll be flat enough, and that's what they were asking for in F. But they were as usual, they're pretty clumsy about the whole thing. Okay, what's next? Now we switch right over to a rod. And yeah, these we're assuming that the distances here are all kind of the same. So they have an equal arrow, E vector, and it's looking like these are all the same. So they have equal but smaller E vectors. And so how does the magnitude? Okay, it said force vectors, excuse me. Well, remember, the closer you are, the greater the force vector. So A is stronger because it's closer. And how does suppose the charge on the pitfall were halved with the force change, yes, because we know it's proportional to Q1 times Q2. Would the ratio change? No, because it's linear in either Q. So if I have one, you gotta be careful. If I have the test charge, then the ratio of the two would stay the same because we'd be changing it. So there is a little subtlety here to be careful of. Equal is proportional to Q of the rod. So if I only change the pith ball, then the ratio would stay the same. We didn't change the Q rod, so that means if I change Q test, then F has to change. And to keep it equal to that all the time, then that means F and Q have to change in proportion to each other. This is a direct proportion, like in this way. F is directly proportional to the test charge. If I write it like this, F is F over Q. Give me a minute. If F over Q is equal to a constant, then F and Q are directly proportional. That's the way to say it. Okay. In this case, if I keep F a constant here, then it's inversely proportional to Q1 and Q2 are in inverse proportion, because if I increase 1, then I have to decrease 2. But that's math. It's a little bit of physics, but it's not the physics of the situation. Okay, with the electric, if not, why not? Right, so since it said with the force change, yes, because if I keep Q2 constant and I change the pith ball, then of course the F will change. Would the ratio change? No, because it's linear in either Q, and I'm only changing one of them, not the other. Yeah, F over Q is the electric field, force per unit charge. And so at A, F over Q is larger than at B because the test charge being the same each time, the force is larger at A, so that means that it's smaller at B with the same Q test. The ratios are different. Sketch the vectors, well, they'll be exactly the same as up here, relatively speaking. What else? What is if the charge in the rod were increased, then F over Q equals to E at point A, that would increase because and I don't know what I have that there for. Oh, I was starting to write it out, I guess. But I would just go here and say, look, I was starting to write the proportional symbol. So F over Q test is Q rod. Of course, we need the R hat over R squared. So if I increase the charge on the rod, yes, E is going to increase over Q is going to increase. If the magnitude of the test charge, no. Let's see, what am I at? With the magnitude of the electric field, no, because electric field doesn't have the test charge in it, and the sign of the test charge. Explain. The magnet is Would the magnitude or direction of the electric field, the test charge? No, because what would happen is it's just proportional of the rod, Q rod. Now, the force, it will change direction, but so will the test charge change its sign. So they'll both become negative, and so it's still a positive. So that means that the magnitude and direction of the E field doesn't change. Okay, so now all these words for a ridiculously easy answer, we know that these are field lines, but if I had I'd have a vector at the equivalent point A, we know it has a certain length, and at the equivalent point B, it's shorter. You know, no big surprise. So if we stare at this for a minute, we notice that the separation out here is greater than the separations in here, and that's how it represents field strength. So now we switch to evenly spaced lines. So in this case, with field lines, notice with field lines, I don't need to know. I did draw these E vectors, but I don't even need to know what is the charge here. And I can just tell without having this here, I can tell what is the strength. And when I go towards this point where they converge, it's stronger. Here, we notice we don't see any source, and that just shows you we don't need to know what the source is. We just know that the spacing here is the same as the spacing there, so the field at both points is equal. Okay, if I have a block of nails, that would just, let's say I have two equal sized blocks. So if I have 1, 2, 3, 4, and 2, 3, 4, so I have a grid of 4 by 4 as opposed to 3 by 3, then there'd be less nails per, if they're the same size block. That means this is a lesser field. Or you just divide by the area. That's a normalizing, that's what normalization means, that you're simply getting a number that lets you compare. So it's better to go not nails per block, but nails per unit area in the block, and then you can get the best comparison. And now they're asking us about if I have a loop, how do I get the most number of nails? Well, I hold the loop, the plane of the loop, perpendicular to the nails, and I can get the most nails in it. And if I hold the plane of the loop parallel to the field lines, the nails, I can't get any of them in. Okay, but if we go back to the plane of the loop, so if we use our A vector, then we would say E and A are parallel, and here E and A are perpendicular. So we also notice that we can just sort of feel to ourselves, if the two vectors are in the same direction, we'll call it positive. If the two vectors are facing each the other way, so I could keep turning the loop over. So once again, that E and A are parallel, but I could define a direction of A. And once you define, that is true. When you have a plane surface, the A vector can actually point either way. So this is digression. But once you pick one way, you can't change in the middle. So that's why I could have my vector lines, I could have my loop, and then in this case now I have the field lines, and now I've rotated this around all the way, and now this is just, in this case, okay, I could have done a better job here, but now I have something like this. Oh, excuse me. Now we gotta add the arrows here, of course. Now the arrows are going the other way. Oh, so in fact, see, I goofed a couple times here. Let's get rid of this. So in this case, now I've got the field lines running the other way, not the loop. And my A is still that way. But let's just, if I were to keep the field lines pointed the same way, and now I've rotated my, from this one here, let's call this 1, and this is 2. If I rotated it around, it doesn't matter, but let's say we rotate it counterclockwise, then the A vector is pointed this way. So this is also negative. And of course, when we're at 90, there's 0. So I can make a little table, and I just went 0, 45, 90, because I know when I use trig functions, cosine sine of 45 is 0.7. Look, we could make this 30 degrees, is it? No, 30 degrees is going to, so this would be 60 degrees, so that's going to be 3. And then 90 and 1, and this is, what is this, 135 and 120. Yeah, 120, so that would be 3. So you know, you could figure this out. That's 5, so 3 is here. Yeah. Anyways, you go from, these would be negative because now the A vector is pointed the other way. So at the end of the day, we came up with the magnitude of E times the magnitude of A times cosine, which is also the definition of a dot product, or a so-called scalar product. The answer is a scalar. When you dot two vectors together, you get a scalar, a single number. Although it's not completely a scalar because it has a minus or a plus associated with it. Okay, there we go. One more down.